Now this heat will be consumed by the system. The part of this heat will be consumed in doing work against external pressure P. So let's say after providing this heat dq, the piston moves upwards and the part of this heat will be consumed in increasing the internal energy of the system. So let's say, suppose initially the temperature was T1. After we have provided the heat dq, the temperature becomes T2, where T2 is more than T1. So this dq is used in two ways. One was used to increase the internal energy of the system, and the other was used in doing work against the external pressure. So this is how we define first law of thermodynamics. Now we'll see what is a isobaric process. In isobaric process, the pressure remains constant. So first we'll see how the graph of an isobaric process will look like, and then we'll derive the expressions for delta U, that is change in internal energy, and the heat supplied. So this is how isobaric process will look like. Since the pressure is constant, so this A and B, this represent the isobaric heating or isobaric expansion. That is, at constant pressure the volume of gas is being increased. Say at point A the volume is VA, and at point B the volume is VB. So here VB is greater than VA. So in this process the gas is getting some heat and it is expanding. So this is isobaric heating or isobaric expansion. Similarly, if the final state is D and the initial state is C, that is, the gas is getting compressed from this state to final state. So this is the case of isobaric cooling or isobaric compression. So in this case the gas is rejecting some heat, and in the process it is getting compressed. Now we'll derive the various relation for an isobaric process. So first we'll derive the expression for change in internal energy. So as we know that delta U is given as F by 2 nR delta T, or we can write it as F by 2 nR T2 minus T1, where T2 is the final temperature and T1 is the initial temperature. Or we can write it as F by 2 nR T2 minus nR T1, or F by 2. Now nRT2 will be equal to PV2 by gas law, and nRT1 will be equal to PV1, since the pressure is same in both the initial state and the final state. So we can write it as F by 2 into P into V2 minus V1, or we can replace V2 minus V1 with delta V. So we end up with this relation, that is delta U is nothing but F by 2 into P into delta V. So we have delta U as F by 2 into P into delta V. Now the work done is given as P dV. So here pressure is constant, so we can take P outside. So P into dV, and the volume changes from V1 to V2. So this is a simple integration. We can write it as P into V2 minus V1, or P delta V. So this is work done. Now dq is given as du plus work done. So du here is f by 2 into p delta v, and the work done here is p delta v. So dq is equal to p delta v into f by 2 plus 1. So these are the various expressions for delta u. This is for work done, and this is for heat exchanged. Now we'll discuss isothermal process. In isothermal process, the temperature remains constant. So since the temperature is constant, there won't be any change in internal energy because it depends on the temperature. And let's derive the equations for work done. So the work done is given as P dV, and we have the gas law, that is nRT is equal to PV. So here the P will be equal to nRT by V. So we can replace P with nRT by V into dV. Now N and R, they are constant, and T is temperature, which is also constant in isothermal process. So we can take nRT outside. So we have nRT dV by V. So we can write it as nRT ln V from V1 to V2. So the work done is nRT ln V2 by V1. And delta U, as we mentioned earlier, is 0 because there is no change in temperature. So dq would be 0 plus W, that is nRT ln V2 by V1. So all the heat supplied is used in expansion, that is doing work against the external pressure. This is how a typical isothermal curves look like on a PV diagram. That is, if we draw the isothermal process on a pressure versus volume graph. Now we can say here that two isothermal curves never cut each other, never intersect each other, and the greater is the distance of curve from the origin, the higher is the temperature. So in this case we have two temperature, T2 and T1. T2 represent this curve and T1 represent this curve. Since the curve represented by T2 is farther from the origin than T1, so T2 is greater than T1. Now we'll talk about the adiabatic process. Adiabatic process is the one where the heat exchange in the entire process is 0. This process is given by the equation PV gamma is equal to constant, where gamma is called adiabatic constant. Now we'll try to derive this relationship. So as we said that total heat exchange in a adiabatic process is 0, so we have dq is equal to du plus W, which is equal to 0, so du is equal to minus W. Now du is nothing but f by 2 nr dt, and work done is p dv. So from gas law we know that PV is equal to nRT, so nr dt will be equal to p dv plus vdp. So we can replace nr dt by p dv plus vdp. So we get p dv plus vdp is equal to minus p dv. Now P dV into F by 2 plus 1 plus V dP is equal to 0, or dV by V 1 plus F by 2 is equal to minus dP by P. Now if we integrate these both these sides, we get ln V into 1 plus F by 2 is equal to minus ln P, or 1 plus F by 2 ln V plus ln P is equal to 0. This is ln P, or we get PV into 1 plus F by 2 is equal to constant. So since F is a constant, which is a degree of freedom, 1 plus F by 2 is also a constant, and we can rewrite this equation as PV into gamma is constant, where gamma is called adiabatic constant and it is equal to 1 plus F by 2. Now we'll see the relationship between temperature and pressure in an adiabatic process. Since we already know that for an adiabatic process we have PV gamma is constant, now we can write this equation as P gamma into V gamma by P to the power gamma minus 1. This will be constant. Now we can write this equation as PV to the power gamma by P to the power gamma minus 1 is constant. Now PV is nothing but nRT, so we can write nR gamma into T gamma by P to the power gamma minus 1 is constant. Now nR to the power gamma will also be constant, so finally we can say that T to the power gamma into P to the power 1 minus gamma is constant. So this is how we can define adiabatic process in terms of temperature and pressure. Now we'll derive the expressions for work done and change in internal energy for adiabatic process. So as we know that change in internal energy, that is du, is given by F by 2 nR dt, or this will be F by 2 P2 V2 minus P1 V1. Now we have seen that 1 plus 2 by F was nothing but gamma, so from here we can write that 1 minus gamma is minus 2 by F, or F is equal to 2 by gamma minus 1. So we can replace F with 2 by gamma minus 1. So we arrive at this equation, that is du is P2 V2 minus P1 V1 by gamma minus 1. As you know that dq is du plus work and dq